Hi, this is Dr. Viv, and in this video I will be discussing the principle of mathematical induction, and this is a set of two videos. The principle of induction states that if a statement S, which is a function of the integers, is known to be true for small values of those integers, that's what I've indicated by saying m less than some value k, and if it can be shown that the statement S as a function of m implies the truth of the statement S as a function of m plus 1, then that statement must be true for all values of m. So this should be thought of like dominoes. If you topple the first domino and that leads to the second domino toppling, and if you can show that if the mth domino topples, the m plus 1th domino will also topple, then it must be true that all dominoes topple. That's roughly what induction says. Let's try to prove the results for that using induction are usually the results that you already know beforehand. So that's one of the slight disappointments of this method. You can really not discover anything new by this. But if you suspect something is true, then you can certainly make some headway into showing that it must be true. So let's try this out. The sum of n integers is equal to n times n plus 1 over 2. This is actually a very celebrated formula because the great Gauss discovered it when he was very young. It is said that he was 5 or 6 around that time, and he was an unruly school child who was not paying attention to his teachers or his fellow students, and he was constantly interrupting the teacher and trying to get the class to be taught at a smarter level. So his teacher asked him to take a slate and sum up the first 100 integers because he figured that would keep him silent for some time. So Gauss, it is said, solved this problem in a few minutes. So let's see how he did it. It is conjectured that he must have done something like this. In his later memoirs, Gauss mentions how he did it. So he first wrote n integers, and then I'm calling that sum S. He wrote the same n integers in the opposite order. So start from the high and go down to the low. And now you simply add them up. So I get 2s is equal to n plus 1. The next term is also n plus 1 because it's n minus 1 plus 2. And you keep getting n plus 1s all the way to the end, which is also n plus 1 there. In fact, you have n such terms. So that means you have n times n plus 1 because there are n of these. And that tells you that S must be n times n plus 1 divided by 2. Beautiful proof by Gauss. Then it was a simple matter for him to put n equals 100 to solve his schoolmaster's problem. So it's 100 times 101 divided by 2. And that multiplication is easy to do without calculators. It's just 50-50 or 5050. Let's now try to prove this result using induction. So the proof goes as follows. In induction, you always have to show the cases for small values. So what I'll do is I'll first write the statement S of m. The statement S of m is 1 plus 2 plus all the way to m must be equal to m times m plus 1 divided by 2. For m equals 1, I will have 1 equals 1 times 2 divided by 2, which is also 1. So that tells you 1 equals 1. M equals 2 is 1 plus 2. Well, 1 plus 2 is 3. What does the right-hand side give us? The right-hand side gives us 2 times 2 plus 1 divided by 2, and that's also 3. So the low cases seem to work out. We're going to assume this and show that the next domino will topple over. S of m plus 1, the left hand side of S of m plus 1 is 1 plus 2 plus m plus 1. Let us see how we can write this. Now it's my custom never to mess with the right hand side. I always only touch the left hand side and then make it come out to be the right hand side. Okay, so that I would like to encourage you to do the same thing, because there are some videos online which mess with both sides at the same time and show that you get equal results on both sides. I don't like that. So I'm just going to focus on this. Here I'm going to use S of m. So I'll get m times m plus 1 divided by 2 plus m plus 1. This can be simplified. M plus 1 is common to both terms, so I can write this as m plus 1 times m over 2 plus 1. And let me try to take the common denominator here. I get m plus 1 times m plus 2 divided by 2, which is exactly the right hand side of S of m, except with m replaced by m plus 1. M goes to m plus 1, m plus 1 goes to m plus 2, and the 2 just remains 2. So we have shown that S of m plus 1 is also true, and by the principle of induction we have established this result for all values of m. So it's pretty amazing that this actually does it. Now I'm going to also do a more abstract example to show you the power of this method of induction. So let's try to establish something that you may have suspected by playing around with drawing. So I want to show that n times n minus 1 over 2 lines connect n points. Now you can only have a line connecting 2 points. You cannot have a line connecting 1 point. So n in this case must be bigger than or equal to 2. Let's try to prove this using induction. Induction can be used to prove all kinds of things, and this is an example of a geometric statement that induction can be used. Let's try the base case of 2 points. Between 2 points, how many lines can be drawn? Well, there's only one line that goes from one point to the other point. So that's n equals 2. 2 times 2 minus 1 over 2, which is 1. Okay, the first base case is valid. The next case would be n equals 3, because there are 3 points. Well, you can draw lines between 1 and 2, 2 and 3, and 3 and 1. So those are 3 lines. Let's see if our result agrees with that. When n equals 2, I'm going to get n equals 3 now. I'm going to get 3 times 3 minus 1 divided by 2. 3 minus 1 is the same as 2. So those two things cancel out and I just get 3. So that's true. The result seems robust. Let's proceed to show that it's true for all values. So the inductive, the first thing we need to do is formulate an assumption. So we'll assume S of m, and S of m is a statement that between m points, m times m minus 1 over 2 lines can be drawn. With this assumption, we're going to see if S of m plus 1 is valid. What does S of m plus 1 look like? If I draw m plus 1 points, I can do it as follows. I can take m points and encase it in something I call the point cloud. in that point cloud, because of S of m, I will have m times m minus 1 over 2 internal lines. Okay, so I'll call these internal lines. Now, into this picture is brought the new point, the m plus 1th point. I'll keep that here. I'm labeling that point as m plus 1. The points here are 1, 2, all the way up to m. Okay, the m plus 1th point is brought in. How many fresh lines can be drawn? So if you have the m plus 1th point, it can draw one new line to every other point that's already there. So it puts out feelers, and there are precisely m feelers it puts out, because it needs to go from the first point to the second point to the third point and all the way to the mth point. So there are precisely m new lines. So the total number of lines we have are going to be these m new lines, the feelers that it puts out, plus the m times m minus 1 over 2 internal lines that exists already within the point cloud thanks to S of m. Let's simplify this. M is common, so I can pull out m, and I end up with 1 plus m minus 1 divided by 2, and that is m times 2 plus m minus 1 divided by 2. So this is m times m plus 1, because 2 minus 1 is 1, divided by 2. It doesn't look immediately like I have shown the result, so let me write it in the following fashion. I'll write m plus 1 first and then m. And m I will write as m plus 1 minus 1. Well, that's certainly true. And now it looks like we have proved it, because all I did here to go from S of m to S of m plus 1, I replaced m by m plus 1. So now we have shown this result is valid for all values of the integers. So in this way, we have shown something very geometric and pretty nice using the principle of induction.